Okay, I'm going to do a few extra practice problems taken from the exercises in the book to review for the final exam. The first problem is 9.53. A random sample of 200 voters in a town is selected and 114 are found to support an annexation suit. Find the 96% confidence interval for the fraction of the voting population favoring the suit. All right, so we see that we're looking for the fraction right here, the fraction of voting population favoring the suit. So that fraction there is telling us that we want a proportion. So we're looking at P, the population parameter P. So from the data, we can calculate P hat. We get that from the random sample of size 200. So we have N equals 200, and there are 114 of them who are in support of the suit. So we have P hat equals 114 divided by 200, which gives us 0.57. From that, we can also calculate Q hat, which is just the complement, or 1 minus 0.57, and that gives us 0.43. So we want a 96% confidence interval, so we're going to take a look at the standard normal distribution. We are looking for cutoff values to find our critical Z statistic so that we have 96% of the area in the middle. That leaves us 0.04 to share between the two tails. So we have 0.02 down in the bottom and 0.2 up in the top. So we're going to look up on the Z table for this value here. We're going to look up 0.98 because of the area to the left of that point is all of this, which is 0.02 plus 0.96, which gives us 0.98. So when I look up 0.98 on the Z table, I get a critical Z value of 2.05. So to calculate our 96% confidence interval, we take P hat plus minus our critical Z value times the standard error of P hat. So we have 0.57 plus minus 2.05 times the square root of P hat, 0.57, times Q hat, 0.43, divided by N, which is our total sample size of 200. What we end up with is 0.57 plus minus 0.072, or if we want to rewrite it nicely, we go from 0.498 to 0.642. Part B. What can we assert with 96% confidence about the possible size of our error if we estimate the fraction of voters favoring the annexation suit to be 0.57? So this is kind of just interpreting our confidence interval. And since up here we can see that we have a P hat plus or minus a certain error, that's what it's talking about, that error. So since 96% confidence interval is 0.57 plus or minus 0.072, what we can say is that we are 96% confident that the error is less than or equal to that 0.072. Part C asks, what sample size would be needed to ensure an error no greater than 0.02 with 96% confidence? And here we're going to assume that we had prior data, and that prior data gave us a p hat of 0.57. If we were not given a p hat, a prior p hat, we would go with the most conservative estimate and say that p hat equals 0.5. So to ensure that the error is no greater than 0.02 with 96% confidence, we are going to set our error term to be less than or equal to 0.02. Since we're talking about a 96% confidence interval, we're going to use our same critical Z value. We're going to plug in the 0.57 because we assumed prior data of 0.57. Q hat is just its complement, and we divide by N instead of the 200 that were given in our problem, because we want to know what sample size would we need to get a smaller error term of only 0.02. So we take a look at this formula and we solve for n. And when we solve for n, we get n is greater than or equal to 0.57 times 0.43 times 2.05 divided by 0.02 squared. So all I did was rearrange these terms and solve for n, and we get that n is greater than or equal to 2,576. All right, the next problem, 10.38. A UCLA researcher claims that the average lifespan of mice can be extended by as much as 8 months when the calories in their diet are reduced by approximately 40% from the time they were weaned. The restricted diets are enriched to normal levels by vitamins and proteins. Suppose that a random sample of 10 mice is fed a normal diet and has an average lifespan of 32.1 months with a standard deviation of 3.2 months, while a sample size of 15 mice is fed the restricted diet and has an average lifespan of 37.6 months with a standard deviation of 2.8 months. Test the hypothesis at an alpha of 0.05 level of significance that the average lifespan of mice on this restricted diet is increased by 8 months against the alternative that the increase is less than 8 months. Assume the distributions of lifespans for regular and restricted diets are approximately normal with equal variances. Okay, so first things first, we need to come up with a hypothesis. So we're talking about means, we're talking about two different groups, and here, right here, it's going to describe what hypotheses we need. So if we're looking at the difference between these two diets, between the restricted diet and the regular diet, it says that the average lifespan of the restricted diet is increased by 8 months against that it is less than 8 months. So what we're going to say is that the difference is assumed to be 8 months, and then we're going to say we don't believe that, we think it's less than 8 months. So when we set up our null hypothesis, we see that we have mu1 minus mu2, where we're going to set mu1 to be the restricted diet because we think that that one is they're going to live longer. So the difference there would be the 8 months. And then we're saying that we believe that it's less than 8 months, that difference. So I'm going to go back and find all the information I need from the problem. So taking a look at the restricted diet first, because I want to look at my subscripts for 1. I'm going to go up here and say, so we have, while a sample size of 15 mice is fed the restricted diet, so here we have N1 equals 15. An average lifespan, so average lifespan, that's going to be X bar is 37.6, so we have 37.6 down here, and a standard deviation of 2.8, standard deviation S1 is 2.8. Looking at the other diet, the normal diet, I call it the regular diet, has an average lifespan of 32.1, standard deviation of 32, and a sample size of 10. So we are down here with X bar 2 equaling the 32.1, S2 equaling 3.2, and N2 equaling 10. We have a cutoff value, right? The alpha of 0.05, that comes from a 0.05 level of significance, right there, our level of significance. We have a small sample size, so we note that our samples are less than 30. We were told that we have equal variances, so we're going to use the t-distribution. So when we want to use the t-distribution, we have to know which t-distribution to use, so we need to calculate the degrees of freedom. Degrees of freedom is n1 plus n2 minus 2. So we have 15 plus 10 minus 2 is 23. Since our alternative hypothesis is that mu1 minus mu2 is less than 8, we're looking at a left tail. So here's our t-distribution right here. We have 23 degrees of freedom. We are looking at a left tail area of 0.05. Our alpha is 0.05. So we need to find the cutoff value from the t-table. That gives us 0.05 in the left tail. And the value that gives us 0.05 in the left tail is negative 1.714. So for the t-test, we're going to have to calculate our test statistic, and in order to do that, we need the pooled sample standard deviation, which is the square root of n1 minus 1 times the sample variance for the first group plus n2 minus 1 times the sample variance of the second group divided by the degrees of freedom. So we have is the square root of 14 times 2.8 squared. Remember, we have to square it because we are given the sample standard deviation, not the sample variance, so we have to square it, plus 9 times the sample standard deviation squared for the second group, divided by 23, which is our standard, which is our degrees of freedom. So our pooled standard deviation is 2.963. So to calculate our test statistic t, we take x bar 1 minus x bar 2 minus the difference established in the null hypothesis times the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. So in this case, all the cases that we've looked at so far, d naught has been 0. We just wanted the difference between the two groups. Here, we want to see about the difference between the two groups equaling 8. So in this d naught, we're going to have an 8. So we have 37.6 minus 32.1 minus 8 divided by the pooled standard deviation, which came from here, the 2.963, divided by the square root of 1 over 15 plus 1 over 10. And we get from that negative 2.0667. So we take a look up here and we see where does negative 2.0667 fall, and it definitely falls over here in our rejection region. So since it falls in our rejection region, since it is less than negative 1.714, we say that we reject the null hypothesis and conclude that the difference is less than 8 months. Now let's suppose that n1 equals 35 and n2 equals 30 for the same problem. Since n1 and n2 are now greater than 30, both of them are greater than or equal to 30, we use the z distribution, and instead of, since we don't know what the sigmas are, we use the sample standard deviations instead. So in this case, we're looking at our standard normal distribution, and we're still looking at our left tail, and we still have 0.05 area down in the left tail. And you might remember that the critical cutoff level for a critical z value for having 0.05 in the left tail is negative 1.645. So we are going to look for a test statistic, and we're going to see if that test statistic falls in our rejection region. So to calculate the the test statistic z, it's x bar 1 minus x bar 2 minus d naught divided by the standard error for that difference between sample means, which is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Again, since we don't know the sigmas, we're going to replace them with the s's. So we have 37.6 minus 32.1 minus 8, it's from the null hypothesis, divided by the square root of the sample standard deviation squared divided by n1 of 35, plus 3.2 squared divided by n2, which is 30. And in this case, we get negative 3.3249. It indeed does fall down here, way down here in the rejection region. So since negative 3.3 falls in the rejection region, we reject the null hypothesis and conclude the difference is less than 8 months. I did a quick check and checked the p-values. You could do this on your own to see if you come close. Using the t, the p-value is about 0.025. You might find a range for it, or might just say that it looks close to that 0.025 value in this case. Using the z, so using the t from the previous problem and the previous n's, we get a p-value of 0.025. Using this problem with the larger number of samples, using the z, we come up with a p-value of 0.0005. So we see that with more data, it is a much stronger statement since the p-value is so much smaller. The final problem in my review is number 10.70. Past data indicate that the amount of money contributed by the working residents of a large city to a volunteer rescue squad is a normal random variable with a standard deviation of $1.40. It has been suggested that the contributions to the rescue squad from just the employees of the sanitation department are much more variable. If the contributions of a random sample of 12 employees from the sanitation department have a standard deviation of $1.75, can we conclude that the standard deviation of the contributions of all sanitation workers is greater than all workers living in the city? All right, so we need to first come up with our hypotheses. So you can see from the information given that we're talking about standard deviations. So standard deviation of $1.40, standard deviation of $1.75. The question at hand is the standard deviation greater than of all the workers living in the city. So we're not talking about mu anymore. We're talking about the other parameter, one of the other parameters. We're talking about sigma. So when we're creating our hypotheses need to be based on sigma. So in this case, I'm putting the standard deviations here, and I'm saying that for all employees, our sigma equals $1.40, and that comes from up here. Standard deviation of $1.40. Our alternative is from this question here. Can we conclude that the standard deviation of contributions of all sanitation workers is greater than of all workers living in the city? So that is what we're trying to test, that we believe sanitation workers have a higher variability. All right, so going back and getting the information from the problem, we can see that we have if contributions of a random sample of 12 employees, so we have a small sample here, 12 employees, so n equals 12, we have a sample standard deviation of $1.75, and that comes from here. So this is saying from that sample we have a standard deviation of $1.75, so that is a sample standard deviation. And we are looking at, does it state an alpha? It doesn't state an alpha, but I'm going to give you an alpha of 0.01. Okay, so when we do a test for the variance or standard deviation of a population, we're going to use the chi-squared distribution and a chi-squared statistic. So here is our chi-squared distribution. It's skewed, if you remember. We are going to look in the book or on our table to find the area that gives the right-hand tail a 0.01. And we need degrees of freedom for a chi-squared, and the degrees of freedom are n minus 1. So we have 12 minus 1, which equals 11. So we're going to look at the table where degrees of freedom is 11 on a chi-squared under the column of 0.01, and we find that we get 24.725. So we need to see if we come up with a chi-squared statistic that falls out here in the tail or does not. So here's our chi-squared statistic. It is n minus 1 times the sample variance. Be careful because we are given the sample standard deviation, so we're going to need to square it, divided by the population variance, which is defined in the null hypothesis. Again, we were given the population standard deviation, so we're going to have to square it as well. So we get 11 times 1.75 squared divided by 1.40 squared. And when we do the arithmetic there, we get 17.19. So you should come up here and see that 17.19 does not fall in the rejection region. It's going to fall somewhere down here. So since 17.19 does not fall in the rejection region, we fail to reject H naught. We can also calculate the p-value. So we would look up to find where 17.19 falls on our table with 11 degrees of freedom. And we would see that 17.19 is going to fall between 0.1 and 0.2. So the probability that a chi-squared statistic would be greater than or equal to 17.19 is in between 0.1 and 0.2. This p-value is not less than our alpha value of 0.01. Therefore, we would not reject the null hypothesis.